All vectors have vertical and horizontal components. So just to introduce you to that sort of idea, I want you to think back to when you studied slope. So when we were finding, say, the slope of a line segment, we found that by looking at both the rise and the run of that line segment. So slope has two components, rise and run. And similarly, any vector can be resolved into its perpendicular or rectangular. We call them vector components. So if we have, for example, a vector v, let me just grab my pen here. Sorry, I was just thinking there for a second. If we have any vector v, we can resolve that then into its horizontal, we'll call that vector x, and vertical, we'll call this vector y, components. And we'll call this angle theta in the corner. So vector v at an angle of theta to the horizontal is the resultant or sum of its perpendicular components x and y. Now to determine the magnitude of that vector, you can use the Pythagorean theorem if you know the magnitude of the other two vectors. And that would be similar to what we did in the last example of your previous lesson, the riverbank example, or crossing the river example. And since you know the direction of the vector v relative to x or y, you can also use trigonometry to determine the direction or magnitude of the other vectors. So for example, looking in this triangle, which is a right triangle, I know that cos theta is equal to the magnitude of x over the magnitude of v, so adjacent over hypotenuse, just to jog your memory. And then if you multiply by the magnitude of v on both sides, you come up with a formula for finding the magnitude of the horizontal component of your vector. And similarly, sine theta would be the magnitude of y over the magnitude of v, and multiplying by the magnitude of v on both sides gives you a formula for finding the vertical component of your vector. So in our example, it says determine the perpendicular components for the following vectors. 250 newtons on a bearing of 50 degrees. Now, let's draw a picture of what that would look like. So a bearing of 50 degrees means 50 degrees from north. Actually, I'm going to use a different color for that. So here's our vector. Okay, so it's on a bearing of 50 degrees from north. And the magnitude of our vector is 250 newtons. Now, draw in the vertical and horizontal components of your vector. And normally we do that by creating a triangle with the x-axis, okay, even though this is north and east, but you could think of that as the x-axis. And then we are asked to find the perpendicular components. So using the formulas above, we know that we can find the magnitude of our horizontal component. Oh, better try this again. That's a little better. By taking the magnitude of our vector and multiplying it by cos theta. Now theta will be this little angle inside our triangle. So if the vector is on a bearing of 50 degrees, then the angle inside the triangle would be 40 degrees. In other words, they're complementary angles, so they have to add up to 90. So the magnitude of x can be found by multiplying 250, which is the magnitude of our vector, times cos 40. So the horizontal component is approximately 191.5 newtons. That would be your horizontal component. And to find the vertical component, you'll take the magnitude of your vector and multiply it by sine theta. So 250 times sine of 40 degrees tells us the vertical component in our vector is 160.7 newtons. Okay, we'll try another one. 120 kilometers per hour on a bearing of south 80 degrees east. So now we're looking in quadrant 4 then for this question. So south 80 degrees east would be about here, meaning inside our triangle we would have an angle of 20 degrees. So we're going to complete our triangle. So this would represent our vertical component and our horizontal component. Now we also know that the magnitude of our vector is 120 kilometers per hour. Now, when finding the horizontal component, once again, the magnitude of x is equal to the magnitude of v times cos, in this case, 20. So I guess I could have filled in the 120 times cos 20. So your horizontal component is 118.2. And your vertical component is 120 times the sine of 20 degrees. So our vertical component is 20.8 kilometers per hour. Now we'll get into more specific applications, but just to get you thinking, in most of these types of word problems, for example, one component will be, say, the speed of the plane or the direction the plane is flying in, and the other component could be the wind resistance that you're up against, or that is, if you're flying in the direction of the wind, that's helping you actually to go a little bit faster. So the components usually represent different forces like that, say gravity, wind resistance, and so on. But for right now, we're just trying to get used to some of these formulas and concepts, and then we will apply them to some specific situations before too long. Here's one sort of straightforward example. It says a cable exerts a force of 350 newtons at an angle of 27.9 degrees with the horizontal. Resolve this force into its perpendicular components, which means find the vertical and horizontal components of that force. So you've got a force of 350 newtons acting at an angle of 27.9 degrees to the horizontal. So we could draw a picture of that as so. And we want to resolve this vector into its horizontal and vertical components, which would be here and here. Okay, so we'll call those x and y again. And then we're going to go through the same process. So when we're finding the horizontal component, we know the magnitude of our horizontal component vector will be 350 times cos 27.9, which comes out to 309.3 newtons. And the vertical component will be 350 times the sine of 27.9, which comes out to 163.8 newtons. And last example says Alec drove 8 kilometers east and then 6 kilometers north. Draw the perpendicular component vectors and the resultant vector r. So if he drives 8 kilometers east and then 6 kilometers north, then his resultant vector would start where he originated and end where he ended up. So we're calling that vector r. Now in part B, it says calculate the magnitude and direction relative to the horizontal vector of the resultant vector. So we'll call that angle theta. So first of all, we'll find the length of r, so the magnitude of our resultant vector, using Pythagorean theorem, since this is a right angle triangle. So we know that the magnitude of r squared is equal to 6 squared plus 8 squared, which is 100. So the magnitude of our resultant vector is 10, the square root of 100. Now, when finding theta, we now know all the lengths of all three sides of this triangle, so I could use sine, cosine, or tangent. I'm going to choose to use the values that were given, just in case we made a mistake when we found the magnitude of the resultant vector. We don't want to carry that mistake forward. So let's use the angles, the side lengths, that were given, so the opposite and adjacent. So we know that tan theta is 6 over 8, and if you use your inverse tan function, you can find the measure of angle theta. It would be approximately 37 degrees. So therefore, the resultant vector has a magnitude of 10 kilometers and acts at an angle of 37 degrees to the horizontal. And that concludes your lesson.